All right, let's dive into Chapter 7 of one of the all-time classic textbooks, Vector Calculus by Marsden and Tromba. Now, this isn't just any old chapter. It's been called the book's technical climax, and for good reason. This is the moment where calculus really grows up, where it breaks free from the straight and narrow, and finally learns how to handle the real, messy, curved world we live in.
So let me ask you this. Picture a satellite whipping around the Earth. Gravity is constantly doing work on it, right? But its path isn't a nice, simple straight line. It's a curve. How in the world do you calculate the total work done by gravity over that orbit? Your standard first-year calculus, the kind that lives on a flat x-axis? Yeah, it just completely breaks down here. We need bigger tools. And that's exactly what we're about to build. So here's our game plan. First, we'll officially move beyond the straight line. Then, we'll figure out how to integrate along a curvy path. After that, we'll level up to mapping complex surfaces. And then, you guessed it, integrating over them. And we'll tie it all back to some amazing real-world applications and see how this all sets the stage for the most beautiful ideas in vector calculus. All right, first things first, we have to fundamentally rethink what an integral is even capable of. You probably remember that a basic integral is all about adding up tiny little rectangles under a curve along a straight line, the x-axis. But what if your axis isn't a line at all? What if it's a winding road or the curved dome of a stadium? Well, we're about to generalize that core idea, breaking the integral out of its one-dimensional prison and letting it loose in 3D space. Okay, so our very first step up this ladder is learning how to integrate along a curve. Think of it as a one-dimensional path that's free to twist and turn anywhere it wants in 3D space. And for this, our first tool is called the path integral. The most important word to remember here is scalar. A path integral is all about summing up a scalar field, that's things like temperature or density, quantities that are just a number, no direction, along some curve. So for example, if you had a piece of wire whose density changes from point to point, a path integral is what you'd use to find its total mass. Simple as that. But then we have the line integral, and this is for vector fields, where every single point in space has a value and a direction. Think of a wind map or a gravitational field. And this, right here, is the tool that directly answers our satellite question. A line integral is precisely how we calculate the work done by a force as an object moves along a curved path. So let's put these side by side, because this is a really crucial distinction. A path integral adds up a scalar quantity, like mass. A line integral adds up the effect of a vector field, like work. And you can see the difference right there in the symbol. See that dot product in the line integral? F dot ds? That little dot is everything. It's the mathematical magic that makes sure we're only counting the part of the force that's actually pushing along the direction of the path. So cool. Okay, we've handled one-dimensional paths. Awesome. But now we need to level up. How do we take these ideas and apply them to two-dimensional surfaces? Well, before we can even think about integrating, we have a whole new problem to solve. How do you even describe a curvy surface in the first place? The answer is this incredibly clever technique called parameterization. You can think of it as inventing a custom-made coordinate system for any surface you can imagine. It's like a flexible GPS that can wrap around a sphere or a donut or, well, anything. It's the engine that makes all of this possible. And this diagram from the book shows it perfectly. See how it takes that simple flat rectangle with its nice UV grid and basically projects or wraps it onto that curved surface in 3D. By doing that, we've given every single point on that complex shape a unique two-part address. It's literally like assigning longitude and latitude to every point on a globe. Now, there's really only one rule for this to work. The surface has to be what we call regular, or more simply, smooth. All that really means is no sharp corners, no creases, no weird self-intersections. As long as you can imagine a single, unique vector sticking straight out at a right angle from any point on the surface, that's the normal vector, then we're good to go. Okay, so we've got a way to describe a surface. You know what's next? Let's integrate over it. And hey, this might look familiar. Just like with pads, we have two different flavors. A scalar surface integral adds up a scalar quantity that lives on the surface itself, like finding the total mass of a curved sheet of metal with varying density. But the vector surface integral, well, that measures something completely different and totally amazing. It measures the total flow of a vector field through the surface, and this idea has a special name, flux. The key idea with flux, the thing you have to get, is that it's all about flow through. We're not measuring the vector field on the surface.
We're measuring how much of that field, be it wind or water or an electric field, is actually penetrating or passing through our surface. It's a huge concept in physics.
And there are some great intuitive ways to think about it. Imagine you're trying to measure how much air is rushing through an open window. That's flux. Or think about holding a net in a river and measuring how much water is flowing through it. That's fluid flux. A vector surface integral is the mathematical tool that lets us calculate these things with absolute precision.
So we've put together this seriously powerful mathematical toolkit. You might be wondering, okay, so what's the big payoff? What can we actually do with all this? Well, it turns out this isn't just some abstract math game. This is the language of the universe. The entire theory of electromagnetism is written in the language of flux. Fluid dynamics would be impossible without these tools to measure flow. Even in pure mathematics, these integrals are how we uncover the deepest, most fundamental properties of shapes. This is the bedrock of modern physics and engineering.
All right, let's bring it all home. Because Chapter 7 isn't just a tough chapter we have to get through, it's the launchpad for some of the most profound and elegant ideas in all of mathematics.
And you don't have to take my word for it. One analysis of Marsden and Tromba's book calls this chapter, and I quote, "the technical climax. This is where all the heavy lifting gets done, where we build the machinery we need for the grand finale." Every single thing we've talked about, path integrals, line integrals, parameterization, flux, all of it comes together as the essential building blocks for what comes next. They unlock the next chapter, which is home to the big three: Green's theorem, Stokes' theorem, and Gauss's divergence theorem. These are some of the most powerful and just beautiful results in all of math, and they are completely out of reach without the foundations we just built. Which leaves us with one final and really profound question. We now know how to integrate over a region, whether it's a surface or a volume. And we know how to integrate along its boundary, whether that's a curve or a surface. But is there some kind of deep connection between the two? Is there a fundamental relationship that links what's happening inside a shape to what's happening on its edge? Well, the answer is a resounding yes. And that connection, it's one of the most beautiful secrets in all of mathematics. And we'll uncover it in our next explainer.